Okay. So you can start presenting now. So, I mean, this is not your final presentation. This is just so that I can get an understanding. Whatever you have done, you can present, and uh, if you got stuck somewhere, you can ask. Yes, it is visible. No, you're not audible, are you? You're still not audible.
I think you have to reconfigure in your driver settings. It keeps happening even on my end.
Okay, so Harsh, you can try fixing this issue. Meanwhile, Mujid, you can start. It doesn't matter if you do not have much, you can start. And, the final
Actually,
presentation is anyway going to be on Monday.
yeah, like actually, I didn't really start preparing much.
Uh-huh.
Uh, Wait, let me share my screen. I'll tell you what was going on all this while. So I still haven't downloaded MATLAB. I was downloading MATLAB, and okay, I had a few questions. I really couldn't like. I didn't attend the second lecture, so that's why a lot of things I missed out. And then when I started watching the second lecture, everything started making sense.
Okay.
So and so then last night I was going through the paper, and I wasn't even yeah, I was able to understand a little bit of the abstract, but so I went back and I relearned everything, exactly what the relation of Reynolds number and all that. Like I completely lost a grip on the basics. So I went back and I revised all of that. And so yeah, wait. And this, I wanted to know what exactly is dissipation scalings and this dissipation constant, because this is the first time I'm hearing this constant.
Okay. So this thing was discussed in third lecture. Can
Hmm.
go back to it, but also briefly. So in turbulent flows, there is production of turbulence at large scales,
Hmm.
and the dissipation happens at small scales. So the dissipation happens at small scales because the gradients are large at smaller scales. So
Okay.
if you look at the expression for dissipation, it is mu times your velocity gradient squared.
Mu
Okay,
times
so
your okay, okay. Hmm.
okay, so mu is the kinematic viscosity. Now your velocity gradients are much higher at small scales. Okay.
Okay. Uh-huh.
Uh,
So, and what I understood about this, so as you said, let's have and on this in today's class, in today's session, we'll discuss what we understood about the paper, right? So, what my grip on this is like when I watched your this second lecture, also I got to I think here, yeah. So I understood like this, the database and all that, and how to get the data using the MATLAB and all. So, and another thing was, so basically, in a turbulent, I mean, for example, in a channel flow pipe, here you have put some. I think there's some pytot or something. No, I think it was this one. Yeah, you place a pytot and which picks up I think the frequency, right? Am I right?
Yeah, pitot measures the flow
Okay,
velocity.
Peter. Okay, so measures the flow velocity, and I even picked up that here you only select a few like you segregate uh, certain velocities which will mess up the simulation. I don't know where was it that I lost. Hold on a minute. Okay, maybe that I was mixing up something else. What is this hot wire anemometry?
Okay, so these are experimental tools. So both pitot probe and hot wire anemometers, they are used to measure velocities. Now, I mean, if you pick up a standard fluid dynamics textbook,
Mm,
you'll find a description for pitot tube. So
okay.
pitot tube measures the fluid velocity by measuring the stagnation difference between stagnation pressure and static pressure. Okay, let me see if I can describe this. I'll use my tab to join in. Okay, so okay, I'm here, right?
No, I still can't see your screen though.
Sorry,
No, are you sharing the screen? Because I can't
I'm
see it.
about I'm about to. It's taking time, so wait for a few minutes.
Sorry. Okay. So meanwhile, it was the first paper I was talking about. It says band pass filters. What exactly is band pass filters? Hello.
Am I audible?
Yeah, you're audible.
Okay. So the first thing you asked was about scaling.
Yeah.
Okay. So, like I said, there is production happening in a turbulent flow, and then there is dissipation of this energy that has been produced. Okay. Now, if you remember, the expression for production was something like this. So you have your Reynolds stresses multiplied by the mean velocity gradient. Okay. Now, if you look at this dimensionally, your velocity fluctuations are of they are of the same order. Okay, so I can write these as u prime. So what I'm doing is I'm seeing of what order this is going to be. Okay, so if in a turbulent flow, let's say let's talk about a channel flow itself. So your mean flow velocities would be something like this. So it's one here at the center, right? Normalized mean flows. Okay, so it's one here and zero at the wall. And if you plot the RMS plot, you'll see that it peaks somewhere here, drops to some value, then again peaks, drops to zero at one. Okay, so the peak value is somewhere around of the order of 10 to 12%. 10 to 12% of this mean value. So they are all of the order of u prime. They are all of the same order. And the for the mean velocity gradients, this xj, this will be of the order of large scales. In this case, it is the channel height or channel half height. So for large scales, we will be using a length scale of L. L is the integral length scale. So this we will use as length scale corresponding to the xj here. Okay. So is this clear or is this confusing here when I'm talking about the order of these variables?
Yeah, I think I'm getting a grip of it.
Okay. So now if you look at the order of your turbulence energy produced, this will be of u prime cube by L, right? Okay, because this is of the order of u prime, this is of the order of u prime. The del u is also of the order of u prime. So this will give you u prime. The numerator would be of the order of u prime. Likewise, the denominator will be of the order of L. Well, L is the integral n scheme. Okay. Now, since all the turbulence energy that is being produced, it will cascade down to smaller scales through that Richardson's cascade or Kolmogorov's cascade, and all of this is being dissipated at small scales. So your production and dissipation are will be equal or of the same order in some sense. So your dissipation is also of the order of u cube by n. So let's say it will be proportional to this thing. Okay. So when you talk about scaling, so what this means is, or let's say, when you scale your dissipation, we're using u cube by L because it is of the order of u cube by L. You should get some constant. This is what the dissipation scaling is. So there is that paper on dissipation scaling. No?
Mhm.
Okay, so this is what the dissipation scaling is. So this is what they have written as C epsilon, and this is what they are checking with Reynolds numbers. Okay, so they are basically studying the variation of C epsilon in a channel flow. So what they have is in a channel flow, uh, they are calculating dissipation at all y locations. So if this is y equal to 0, the wall is y equal to 0, and this would be y is equal to h, that is the channel half height. So from y equal to 0 to h, so this is y from 0 to h. What they are plotting is, uh, first they are plotting the C epsilon, that is the dissipation scaling constant that should be there. Then they are also plotting something called Reynolds number based on Taylor's microscale. Okay. Okay, so I also explained this in the last class, what Taylor's microscale is and what the definition for Reynolds number is. Oh, okay, so they plotted this Reynolds number, R lambda, as a function of y again. Okay, so at each y you have some R lambda, and corresponding to this you have some C epsilon. So using these two, they have plotted C epsilon as a function of R lambda, and they have made comments on how this scaling of dissipation, which depends on this constant. Where is this constant? So, which depends on this constant, how this scaling behaves with Reynolds number. So that is what their work is basically. Okay. You also asked another question. Side
Yeah,
scaling.
what exactly is band pass filters?
Yeah. Okay. So uh, let's say you have some function in your spatial domain. Okay. So I mean, usually in your DNS you have your spatial domain x, y, z, and you have your velocities as a function of x, y, z. So x, y, and z. So your u is a function of x, y, z. Okay, so this is in spatial domain. Okay, if you go in, if you take the Fourier, if you take a Fourier transform of this velocity, okay, um, you'll get your velocities in vectors in wave number space. So you'll get u as a function of k, um, and if you plot the energy spectrum of this thing, if you remember what energy spectrum is, uh, the power. So there is something called power spectral density, and there is energy spectrum. So I talked about power spectral density, but if you take the Fourier transform, if you take the Fourier transform and plot the square of these coefficient of this Fourier transform as a function of k, you'll get the energy in U. Okay, so you're basically plotting the square of these. So it will have some content. So likewise for any, not just velocity, any function of. So if you take the Fourier transform of some function which is in space, you'll get in Fourier domain it will be a function of wave numbers, and if the function is of time, if you take a Fourier transform you'll get it in frequency. Okay, so you'll get either this, you'll get f hat as a function of k or as a function of omega. So this has some spectral content. Okay, now there are several filters here. What filters do is they essentially filter out these spectral contents. So there is, there is low pass filter. So what this means is it allows only low frequencies to pass through this filter. Okay. So what happens is if this is your spectra of your function in Fourier space, it can be either k or omega. So if you apply a low pass filter at some cutoff frequency kc or omega c, okay. So what the filter will do, it will only allow frequencies which are lower than this. So let's say if this is kc or omega c, so this filter will only allow frequencies that are lower than this. So when you apply this filter, the modified spectra would be something like this. So it will basically cut off your spectra here. Now the curve that I've drawn is for an ideal filter. Your actual filters will not have such sharp cutoffs, but this is what conceptually it is. Likewise for a high pass filter. So you have a high pass filter as well. Your high pass filter will allow only high frequencies. Okay, so you have your spectral content k omega, and what this will do, it will allow only these higher frequencies to remain. It will filter out all these lower ones. Okay. Then you have band pass filters. So what band pass filter does is it allows frequencies only in a particular band. So you have a spectral content here. Okay, these plots are linear. These are not, I'm not plot for representational purposes. I'm plotting, these plots are linear in nature. Okay, these are linear plots. So again, you have your spectral content. What a band pass filter would do is that it will allow frequencies in a band. So this is the band of frequencies that it is allowing, and it filters everything outside this band. So is this clear now what a band pass filter is?
Okay, I understood, but what is the purpose? Like, why are we using this? Is it because it will mess up the final result, or what?
Okay, so it is, you know, uh, so the purpose is to look at the spectral content. So, uh, you know, in one of the lectures I talked about turbulence being composed of eddying motions.
Yeah.
Yeah, eddying motions or scales. So, composed of eddies. Okay. I also talked about scale of these eddies. Scale, that is some length scale associated with these eddies. So, I mean, if in a turbulent flow, if you measure the spectra, if you measure the velocity and calculate the spectra, what the spectra basically shows is what are the energy content across various eddies of across eddies of various scales. So this k, the wave number, this is basically 2 pi by L, where L is the size of that eddy, a representative size of that eddy. Okay.
Mm.
So what this curve basically shows is in your turbulent signal, what is the energy content corresponding to a particular wave number or particular length scale. Let's say if you want to look at the energy content of some small scale, let's say at Kolmogorov scales. So if you want to look at uh, uh, the energy content of scales which are of the order of eta. Eta is the Kolmogorov scale. So you'll find the corresponding wave number k eta, which is 2 pi by eta, which will be somewhere here. Since eta is very small, your 2 pi by eta or k eta would be very large. So it is somewhere here. This is your k eta, and this gives you the spectral content or the energy at this wave number, e eta. Okay. Okay. So what the spectra represents is what is the energy of how the energy is distributed among these eddies. Okay, if you go at large scales, let's say integral length scales, then the wave number corresponding to that would be 2 pi by L. Now L is basically, of course, large scales are, so the L would be large and the corresponding KL would be small. So the corresponding KL is here. Okay, and this plot will show you how much energy this length scale has. So this is what the spectra shows. Now when we apply filter, what we are trying to look at is, we are trying to look at the spectral content, or we are trying to isolate the, the effects of eddies of a particular size. If you understand what Fourier transforms are, basically, if let's say your signal is sinusoidal in nature, okay, you have some sine wave of uh, frequency omega. Let's stay in x. Okay, so if your velocity is like this, if you take the Fourier transform of it and plot the spectra, you'll get a peak at 1 omega. So let's say if this is omega 1, you'll get a peak here. You'll get a peak here, and at other places it will be 0. Now, if your UX is composed of two eddies, you have your sine omega 1x plus there is, let's say a higher frequency wave superimposed on it. Let's say 5 times omega 1x. So what this is basically, this red part is that you have a high frequency wave which would add to this. Okay, so it will, your velocity signal now will look something like this. Now if you take the Fourier transform, it will have two peaks. One is at omega 1 and the other is at 5 times omega 1. And it will also show how much energy it has. So the energy would correspond to these coefficients. So if your velocity signal is defined as such, the energies at these frequencies would be related to these coefficients. Okay. Now, what happens in a turbulent signal is, or if you remember what Fourier transforms are, you can approximate any function using a you can approximate any function using a Fourier series or a Fourier transform. So that is what we do in turbulent flows. So when we plot a spectra like this, what we are basically trying to say is, uh, what kinds of sinusoids are present and how much energy do they have? How much is their contribution towards the velocity? Is this clear?
Okay, okay.
Yeah.
Mm.
Okay. So when we filter out, we basically isolate these frequencies. So let's say if I put a band pass filter here on this thing, so this will isolate this blue curve here for me. It will filter out the higher frequencies, and I'll be left with only this thing. Okay.
Basically smoothens the curve.
Yeah. Basically smoothens the curve or isolates the effect of a few particular eddies.
Okay.
So if I put a band pass filter here in this range, so my entire velocity field has contributions from all the frequencies in this range. But if I put a band pass filter now, the velocity field that I would get will have contributions from only these eddies. So it basically filters out the effect of these eddies. So that is what band pass filter is. So if
Okay.
you look at that paper, what it does is it uses these band pass filters and looks at the structure of those eddies. So if you want to look at large scale structures, so the wave number corresponding to those structures would be lower. So if you will put a band pass filter here, and you'll see what the structure of those large scale eddies are. If you want to look at the small scale eddies, we'll put a band pass filter here, and then you can study the structure of these these small scale eddies. So that's what band pass filters are. Okay,
So
hope this
now
is clear.
our the assignment is basically we collect the data and we make this generate the simulation based on the data we get from that database, right? The John Hopkins database.
Yeah.
So I don't know. Last night, for some reason, I thought we are getting the data. So what if we explore some? What if we explore some like machine learning and all that? So I started reading a book on this like intersection of fluid mechanics with machine learning. So that's why I couldn't complete the assignment. But because although I am fulfilling the objective of the assignment to explore new things, but I know I still haven't done my assignment. But the next time we have a session, I'll definitely like complete the assignment by then.
It's okay. It's okay. So it's not like you have to do this assignment itself. So the objective of this course was that, like you said, you needed data for that machine learning thing that you wanted to do.
Yeah.
So the objective of this course was that you would be able to get that data yourself, to generate that data yourself, and that's why I talked about that open source John Hopkins database and also the Incompact code. So that's what the objective of this code is. that you'll be able to generate your own data. It's okay if you want to do machine learning. In that case, I'll be more than happy if you present your project or whatever your vision is with that project. And you tell me what project you want to do, and once you have your data, what you are going to do about it, how you're going to use that data. Okay. So you can do that as well.
Yeah, so now finally it's the weekend and I have some time. So I'll today and tomorrow I'll put my work on it.
Okay, yeah, it's okay. So you'll be continuing with this bandpass filtering thing, or you'll be doing that machine learning thing?
I most likely I'll do this band pass filter thing because the textbook which I went through, right?
Yeah.
It's really long. It's like 500 pages. I still there's a lot of interesting stuff here. Wait, hold on. So there is a lot of interesting stuff here, but wait, hold on.
This is the machine. Okay, data driven science.
Yeah, so this professor he's very familiar with implementing machine learning to fluid mechanics principles and simulations and all, and he has recorded a lot of lectures and posted on YouTube also. So and one of the YouTube lectures I feel where I forgot that name. There is some simulation. Okay, so yeah, I thought maybe this is something to explore. It'll take a lot of time, but this is something I can look forward to the next time, like once I finish this assignment and all. So that's what I thought.
Okay, it's fine. So for this assignment, what you can focus on is generating that data.
Hmm.
Okay,
Okay.
uh, generating the data and you maybe get some more clarity, but keep that as your priority, that you'll be able to get your own data,
Hmm. Okay, got
or
it.
or even Nexus, that John Hopkins database.
Hmm. Okay.
Okay,
I think Harsh's mic is working now.
okay, Harsh. So you can go ahead now. I had okay. So maybe try putting them in chat box. Yeah, you can write them here. I'll try to answer those. Okay. So do you want me to do it first and then you'll move on to the next question, or do you want to post other questions as well? Okay, okay. I will demonstrate this to you. Okay. Uh, can you see my screen?
Yeah, it is visible.
Okay. Okay, so we will navigate to the folder that I had my in compact installations. Okay. So I assume you had no problems installing the files, just the make command you're facing problems with. Okay. So these are all the files that I get after make running the make command, but let's clean all these. These are the files that you have. So in my case, I have this channel, cylinder, and TBL, turbine, and test. These are the extra folders I have. Otherwise, these are the files that you'd get. Okay. So before running the make file, you need to have installed these GCC compilers. So check if you have these GCC compilers with you or not. Um, okay, let's see how to check this. Okay, so if you have this GCC installed, you'll see something like this. Okay, and let's say if you do not have this GCC, then you do this. Or simply Google how to install these compilers. You have installed them, okay, that's fine. Uh, the another thing that you need to install is the MPI-CH libraries. So I hope you have them as well. Okay. So after that, what I have to do is run this make command. So it will give you a few warnings, but you can ignore them for now. Unless you get an error, it would be fine. So, I mean, does it run something like this, or you do not see anything at all? Okay, so this runs. So the compilation takes time. Okay, so it will take a few minutes. Once it is over, you can use the executable that has been created. Okay, so let this thing compile. Meanwhile, you can ask other questions if you have any. Okay, Harsh, do you have any other questions? Okay. Okay, so the compilation is over. These are the files you'll get. So do you get these files? Okay. So I guess you have problems running the command. Is that it? Okay, so uh, you see this folder called turbine. So this is the folder I have created to run my turbine simulations. So what you do is you make a directory, make a new directory. In my case, I'll call it turbine 2. So we make this directory because this is where all the data will be saved. So you make this directory now. Okay. Yeah. So you make this directory and you copy the input files. So these input files, you'll find them in, the examples folder. So you see this examples folder is there. What I'll do is list out the content of that folder. Examples. Then there is, so for the wind turbine, they have a wind turbine. Um, you copy the input file. So you see they have an input file as well. So in this folder, they have an input file, and for the turbine case, we also have to copy turbines.ad. For the channel flow case, you only need to copy this input.i3d. That's all. Okay, so what I'll do is I'll copy these files. Turbine ad. So this is the path for that file that I want to copy, and now I'll put in the destination where I want to copy this thing. Okay. So if you list out the contents of the turbine 2 folder that I've created now, you'll see that it has copied this input i3d file. Okay, I'll also copy this turbine.ad. Just use the above arrow to repeat this command. Copy this as well, the other file as well. Now I'll go to the turbine folder, the contents. So it has this input i3d file and turbines.file file. Now I'll run my simulation in turbine 2 folder, and it will save all the output data here in this folder itself. Okay, so to run this simulation, I need to write mpi run. Mpi run is the run command. So it will run the executable. Need to specify the number of processors you want to use. So dash.n. And let's say if you're using 8 processors, you use 8 here. And after doing this, you need to specify the path of that executable. So the executable is in the previous folder. It's this file xcompact3d. So you need to specify the path for this. So you get to the previous folder. We use 2 dots for the previous folder. And then we write xcompact3d. And then we specify the input file that you want to use. So the input file is in the present folder itself. So use single dot for that and specify the input file. Okay. Now if you press enter, it will start running this case. Okay, so the simulations have started.
Am I audible now?
Yeah, you're audible.
Okay, okay. There was some problem with the Teams only.
Okay.
Team settings.
So did you get this? How to
Yeah,
run?
yeah, I got this. I'll try this out myself.
Good.
Okay, this will save all the files and then we can run these files, view these files in MATLAB.
Yeah. So this will, so once you run this thing,
Okay,
uh, okay. So I created this turbine too. Uh, your your data would be saved in these three folders. So you have these three folders, right? You have probes,
yes,
out, and data.
okay.
So all your data is in data folder. Okay, I'll show you the output for channel. So again, you have these three things. So all the output is it will be in channel. It's not in channel here. Let's go to TBL. So all the outputs are here. Okay, so these are binary files. You can read them in MATLAB. You can refer to the second lecture I had
Yeah,
given.
yeah, I know how to read these
Yeah.
files, just didn't know how to get these files.
So you can
At
get
that.
these files. So is this fine
Okay,
now?
yeah, yeah. Okay, I'll
Okay.
try this out and let me share my screen first.
Okay.
Okay, is my screen visible?
Yeah.
So these are the files I have. I
Yeah.
did that thing. I ran the make file, and after this, I got stuck, so I did not do anything after
So
this.
you can try it right now if you want.
Okay,
Maybe make a directory for channel flow
mkdir.
space channel.
Do we have to add a backslash or no?
No, no, no. Since you're making a folder right now.
Okay,
So if you type ls again, you'll see that channel folder there. So it's down there in the first column.
okay.
Yeah. So now you have to copy the input files from the examples folder. So if you navigate to examples folder now,
How do I do that? I do not
so
remember the command
I mean,
exactly.
if you want to look at these files, you type ls,
ls
okay, space dot forward slash,
forward slash
sorry, backward slash, yeah, examples. So you type in examples.
examples. Okay, this example, this will go, let me go in the examples folder.
Yeah, so you put forward slash again
Okay,
without space. Uh, Type channel cap with capital C, I guess,
okay.
with capital C. So if you, I mean, if you delete the entire thing, if you remove channel here,
Hmm.
delete channel entirely. Uh, if you press tab twice, it will show you what folders are there in this path.
Okay,
Okay, so
oh,
you see all these folders are there.
okay.
There
This
is
is
one
the
for
first
channel
folder.
flow. So if you type ch and press tab again, it will autofill.
Okay, tick, tick.
Okay,
Now
you can press tab again twice to see what four files are there.
I have
Okay, so
to
yeah, there
input
are
it.
several input files for several cases here. You can use anyone. You can use input.i3d. So input.i3d, this is the file that you want to copy, right?
Okay,
Yeah.
yes.
So if you go to ls is the command to list out all the files that are there. You need to replace ls from cp.
This ls.
Yeah. So you use your arrow keys to navigate to that point, remove that with cp.
Okay, not familiar. This arrow, download arrow thing. Okay,
It's okay. Yeah. And you come here and put a space there with single dot slash. Uh, you give the
where do
you
I
need
want to
to give,
copy it?
yeah,
Okay.
destination. So it's the channel folder that you have created.
Mhm. I have to enter this channel here.
Yeah.
That's it.
Yeah, you press enter and I think it has been copied. So you go to that channel folder.
I go to the channel folder. Okay.
Yeah. So you use CD for that. Check the files here.
Okay. There is input
Yeah.
i3d.
So now you can run it. So how many cores do you have on your system?
I don't know. This is not my system. This is the system I borrowed from
I
my
think
brother.
I think you can check it on Ubuntu and using NCPU.
In CPU.
Let me see if that is. So you
Okay.
type ls CPU.
Right there, or do I have to go back to the
No, you can do it right there.
ls CPU?
Yeah, without space, without space.
Okay.
Okay, so you have 4 CPUs, and there are 2 cores per socket. So you can run 8 parallel processes here. So you
Okay.
type MPI run
MPI run
space -n
dash n
space 8
8.
space double dot. So you have to write the executable path for that executable slash
Okay.
x compact.
X compact.
You can use tab to autofill.
Okay. Take
Yeah, and single dot slash input.
single dash slash input i3d.
Now, if you press enter, it will start running. Okay, you can allow access. But you see that the simulation is running, right?
Yeah. Yeah.
Okay.
Okay. So
If you
this
want to
will save
if, if you want to kill this process midway, you have to type Control
control.
C.
Okay. Okay. And this is the file I've been reading.
Yeah.
So I get the basic understanding of what they're doing.
Hmm.
Like they are calculating these vortices and vortex flow near wall with some specific Reynolds number.
Yeah.
Okay, so what I don't understand here is what is this self-sustaining process? They are saying self-sustaining process here, like at the start.
Okay. Okay. So there is again that is some physics that I'll have to tell you. Um,
Is this like the energy cascading thing? I know that thing. Like,
it is energy cascading, as in there is production happening, right?
yeah,
Uh, so there is a self-sustaining process which keeps that production going on. So there are a hierarchy of coherent structures present in the flow,
okay,
and these coherent structures, they interact in a way such that the turbulence keeps on being generated. So there is something called near wall streaks.
yes,
So these are streaky flows. Uh, so these streaks, they are being generated by these fluctuations or these disturbances. So these streaks are generated, they lift up away from the wall, they undergo instability, and then they break down. So this breakdown actually generates turbulence. And the generated turbulence, so the fluctuations that are created by this, the breakdown of that streak, they in turn give the inputs for the formation of new
next turbulence.
streaks. Yeah,
Okay,
for the formation of new streaks. So there is this self-sustaining process that goes on in a boundary layer, in a turbulent flow. So the streak generation, their lift up and their breakdown. So I guess they might have also mentioned that somewhere. If you scroll through it, you have to scroll down. So wherever they have mentioned the self-sustaining process
Okay.
first.
Self-sustaining process. I have read till here. I understand what this is. This is like they measured the vortex in. This is very close to wall,
Yeah,
and as far they got vortex became more spherical,
yeah,
but the spherical thing does not show. Where was this? It shows just that they're distributed isotropically.
yes.
That much I
Actually,
understood.
yeah, that's the that's in a sense an average of identified structures over several realizations. Okay, so this is not an individual structure that you would find in the flow. There
Okay.
are several small scale structures, and the thing is, many of those structures are isotropically oriented, so they do not have any directional preferences. So when you
Right.
average out over all those realizations, the average comes out to be spherical. So that's how they say that it is isotropically oriented, because there is no directional preference. However, near
Uh,
wall you see that it's not spherical and there is some directional preference to those structures.
mm,
Okay, so that's what it is. Anyways, you can run the code now, right?
uh, is it done? Yeah, I think.
I guess it is still running. So,
Okay.
so another thing that I want to tell you.
Remaining time 23 hours. It will take so much time. I changed the input file, but
Yeah.
I don't know. Yeah, it was the input i3D. I tried to change some things in it.
Okay.
The where you told me the domain space and
Yeah.
like
Yeah.
the time steps. I decreased the time steps to zero point 0.5 from zero point 0.1. Every half a second, they save one value.
Okay. So the variables that they are specified that are specified in the input files are normalized. So it's not in seconds. It's just time.
Okay, good time. So
Okay. It's just a number. So they are normalized in using some variable. Okay. So uh, uh, anything else you want to ask or present?
will I have to read this more? Most of it is like it is understandable, but
Uh-huh.
all these things are related to other like other studies what someone else has already done. Like here, large scale streaks are also shown by Del Alamo, so I have to
Yeah.
go there, and it is taking a lot of time.
Yeah, that's what I mean. The main thing that you have to focus on is getting the data and starting with some analysis. So in the assignments, I might have mentioned a paper by Kim and Moin,
Yes,
1987.
yes,
Okay, so it's okay. I mean, these papers are just to show you, just to give you an example of what kind of research is happening right now. You do not have to reproduce these results exactly. But the
okay,
basic thing that I want you to do is you generate your data and you reproduce those basic plots like mean flow velocities, the your RMS plots, and then compare them with the Kim and Moin's
existing data.
papers. Yeah, so that's the standard we compare with for channel flow simulations.
Okay,
Okay, once you are able to do it, you can maybe try something out of these, or if you have some other problem in mind, you can do that as well. But the basic thing is you generate your data and perform those basic analysis, those validation exercises, and those make those basic plots and then present those.
okay, I'll try that.
Okay. Uh, okay, so we can stop here. If you have any questions, you can get back to me. Uh,
Okay,
and shall we have the next session on Monday?
yeah.
Yeah, it works.
Okay. Okay, then see you on Monday then. Bye bye.
Okay.
Okay.
Bye. Thank you.